I want to show you also about colliding galaxies. We think the Milky Way and the other galaxies have been changed through time by collisions, as this simulated movie is doing. Galaxies come close together. There's a picture there that just happens to match the two real ones in the sky. And then you see they're going to continue to orbit and merge, and now you have a new galaxy of a completely different shape. This may be what happened to our own Milky Way. And we can tell, not only from computers, but also for looking for distant examples that might resemble our own galaxy. We will be looking for supernovae that are a little bit like the ones that blew up in the earliest universe. We think the first stars were much more massive than the sun, hundreds of times as massive, and that it's possible that some of them will immediately produce a black hole when they blow up. Very recently, one sort of like that was found nearby, and it turned out to be much different and much brighter than all the others. So we're still getting surprises, but we hope that there are some sort of like this in the early universe. We once in a while get a star blowing up and sending a jet of material out. Sometimes it aims at us. So this is a supernova in the artist's idea, sending material almost the speed of light. And if you happen to be in the direction that it's pointed, you can see this across the edge of the universe, across billions and billions of light years. So not only is this interesting in its own way, but it also gives us a beacon and a searchlight to understand the most early things in the universe. By the way, these were found by a satellite network that was put up to see if the Soviet Union was cheating on the test ban treaty. You know, we're still fussing about the test ban treaty. But this is one of the remarkable accomplishments of science that came from that. The network of satellites said somebody's cheating all the time. These things are going off quite often. And astronomers were completely shocked. We couldn't understand this. Nobody knew what it was. And some people said, well, they're coming equally from every direction, so they must be coming from the distant universe. But that's a very spectacular prediction, because for a moment, each of those objects is as bright as all the other stars in the sky. And so how can this be that something that far away could be that bright? Well, it just happens when the thing is aimed at us. That's what does it. So a lot of wonderful surprises. Closer to home, we want to see how stars like ours are made. This is one of our most famous pictures from NASA. It's called the Eagle Nebula, and it's a place where stars like that one and that one behind there have just been born. So you'd like to say, well, I think they're being born inside those dust clouds, but I can't see inside. This dust, by the way, is also those same chemical elements that were made inside previous generations of stars. So what are we going to do to see how stars are born inside this cloud? Try using infrared. And this is the same place, and you can see it's very different. The dust is not nearly as opaque, and you can begin to see things that are inside the dust cloud that you couldn't have seen before. So these are newly born stars. Now, this is not necessarily where they're happening now, but other places like this, we can see inside with infrared. We can see planets even. A few have been seen and actually had their pictures taken around other stars. The one I like the best is this one. This one was around a very bright star in the southern sky. These are Hubble pictures. What the Hubble did was, first they said there's a star over here. We're going to block that out. We'll blot that out with a thing where you just don't let the light in. And this is called a coronagraph. And then you see this dust ring orbiting around it. They looked at that and they said that ring couldn't be like that unless something was making it like that. So there must be a planet whose gravitational force is causing that shape. And so sure enough, when they looked carefully, they came back a couple of years later, the planet was there and then it moved. So this is the first time since the discovery of Neptune that people said mathematically, we know it's got to be there, and it was there. It's very cool. We've also begun to learn how to take pictures from the ground. That's a Hubble telescope picture, but these others are taken from the ground with very fancy optics, and they're making progress too. Now here's a quite remarkable process that we now can do. Once in a while, a planet goes in front of a star, blocks some of the light, then it comes back up. Now while this is happening, some of the starlight is actually going through the atmosphere of the planet on its way to our telescope. So that means we can begin to learn about the characteristics of those planets and their atmospheres and get the chemistry, the temperature. If you're really lucky, we hope to even be able to see the presence of moons around other planets. Sometimes the planet goes behind the star. And if the planet is really bright, then you can notice this too, but only for very hot planets. But we got some of those already. We have a catalog now of about 500 of these objects. Most of them have been observed by what's called the Kepler telescope, which is put up just exactly to find these objects. And when they get done in a few years, they hope to tell us, here's a list of stars like the Sun with planets like the Earth. We'll see. I hope they're successful. The search for life. Well, clearly, one way is to study these objects. See if you can find the signs of what we take as sign of life here, oxygen. Oxygen is in our atmosphere. It's there because plants made it. So if you can find oxygen in the atmosphere of another star, and along with things like carbon dioxide and water vapor, you say, oh, that's an awful lot like Earth. If you want to know, is there some other kind of life that doesn't work like ours, we might never know. But at least this kind, our kind, could be detected from tremendous distances because of that specialness of oxygen. So there is really a hope. If you want to look for life in the solar system, there are also places to go. Everybody knows about Earth and Mars. How about other places? There are 4 satellites of the giant planets that are already known to have water, liquid water. So here's one of them. This is Europa. It's the satellite of Jupiter. Galileo saw it. He didn't see these cracks. What this is a surface covered with ice, and there's these, and it's a very active little moon. So we believe that there's liquid water underneath, probably pretty salty, and that these cracks in the surface are letting mud or whatever is coming up from the bottom up to the surface. So you could say, well, how do I know what's there? Well, we might just want to go land sometime and drill a hole. Anyway, a very interesting place to go. It's one of the reasons that this is one of the top targets for outer solar system exploration. So let's see. There's a lot more to tell you. If you want to hear this or see the story of the COBE project and some of what we're doing now, there is a book. I guess all the copies that I brought have been snapped up. You can get them from Amazon for pretty cheap, or in the first edition you can get on Kindle also. So lots of possibilities, but I'm very happy to have questions about anything. And so thank you for coming. Okay, I see hands every place. Let me start in the back.
When is the expected launch of this?
Oh, well, the official launch date's 2014, but we can't make it because we don't have enough money right now budgeted. And so we have been examined very carefully by the review committees that are telling us we need more money. And, okay.
So call your representative.
Yeah, it would be a nice idea. Okay, over there.
The concept, I see that some of this stuff started by adding more terms to Maxwell's equations. And is there a path that you got from that animation of how Earth forms that goes back to Maxwell's equations? Or to what kind of equations generated that picture of the three big, of how Earth formed out of the universe in the early thing, that animation?
Well, the animation that I showed you about the solar system, that's just gravitation.
That's gravitation.
Just ordinary gravity. When Newton told us about the laws of gravity, people looked up in the sky and said, perfect clockwork universe. People didn't know at that time that gravitation doesn't make a clockwork universe because the gravitational forces are unstable. And it's actually now hard to explain how come the solar system has been stable for more or less 5 billion years, because it's very easy. If you start off with a hypothetical solar system, most of them don't end up like the current solar system. So that's interesting and difficult, tricky question. There we go.
You said that the universe expansion started to accelerate about 5 billion years ago. That's right around when our solar system was created. That's a coincidence?
I suppose.
How interesting.
Yeah. It was going to happen sometime.
I hope this isn't too far out, but what sort of evidence would astronomers have to find to support the sort of multiverse hypothesis?
Oh, the multiverse. At the moment, I'm not aware that there's any testable prediction from the multiverse hypothesis. So it's probable that we astronomers will not be able to see anything that would test that theory. On the other hand, sometimes theories do predict something you can see, and they just haven't gotten far enough yet. Mathematicians did predict things that turned out. They predicted antimatter. Dirac's equations had a place for antimatter. That was quite a surprise. And then it was found. And Einstein gave us this possibility of the dark energy, and we thought, oh, that's crazy. But there it is, I guess. So anyway, the multiverse is probably going to be in this category of almost untestable, but sometime we might have a theory that we really like. Right now, we don't have a theory of quantum gravity. We don't know how gravity seems to work, and it's up for grabs at the moment. So when they get there, maybe we'll believe it.
In the same realm, perhaps, as I understand it, the string theorists argue that there are 11 dimensions, or is it 13? Tell us about it.
Oh, well, okay, string theory and the number of dimensions. There are a lot of different versions of string theory. People wonder, what is string theory, and why do we care about stringy things? Just a short story about string theory and why we need it, or something like it. We know how to calculate the energy in the electric field of a particle. Say an electron, we think of it as a point object. It's got an electric field sticking out, and we think there's energy in the electric fields. You add up all the energy that an electron should have from that, and it's infinity. So it doesn't work, right? So what you're going to do? Well, suppose the electron wasn't a point, but was actually a thread. Maybe a very tiny thread, but then it now wouldn't be infinity anymore. So this is a way around the infinities. Richard Feynman and others got prizes for thinking about how to subtract infinity from infinity and get something reasonable. In this case, maybe let's not put the infinity in. Maybe there's another way. So the string theories that people are working on are following this idea and trying to make it work. And how many dimensions do you have to have? So they're getting a lot of progress. It's just we can't tell how soon we're going to get to the end.
It's not been discredited.
No, it's not discredited, but it's also not finished. It's a hard job. When we finally get the answer, people will say, how come we didn't think of that a long time ago? But right now, it's a mystery.